The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Welcome back to those of you who are in part one of our two-part series. If you're new in this session, I wanted to just introduce myself real quickly. I'm Chris Ball. I'm the current chairman of the committee E706, which is Concrete Repair Education. Our committee puts together repair application procedures, which are the documents that we're presenting today. It's just one of the things that we're doing. We're also trying to expand broader than repair application procedures, but more into concrete repair education in general. So if you have an interest in this, I encourage you to come join our committee or get involved. We meet on Sunday mornings at 8 o'clock. No breakfast is included. To coin a term from Fred. But I want to thank all the speakers. The first session was very well attended. We had standing room only, and I'm really proud to see that the level of interest in the repair and rehabilitation industry. The reason that we requested this session at this convention was that this is the 20-year anniversary of our repair application, or it was originally called the RAP committee and morphed into repair education. And so this is a little bit of celebration of some of the things that we've accomplished through the years. So without further ado, I'll turn it over to your session moderator, John Lund, who's a committee member.
So yeah, I am going to be the moderator for this session. We're going to be covering the repair application procedure documents 8 through 14, so the second half. And our first presentation is the gentleman who just was speaking, Mr. Chris Ball, talking about repair application procedure number 8.
Okay. Well, thank you for coming back. Like I said earlier, this is repair application procedure bulletin number 8. Installation of embedded galvanic anodes. The author on this document was David Whitmore. He is unable to attend this session, so I'm going to step in for him as the presenter. So repair application for embedded galvanic anodes. Obviously, where do you use embedded galvanic anodes? You use them in applications where you have corrosion. Galvanic anodes are used as a sacrificial means to provide protection to corrosion of reinforcing steel. And what we're going to focus on this repair application procedure is the application of galvanic anodes that are retrofit into existing structures. So you see a number of pictures there of different types of corrosion issues, and it's kind of spreads the gamut here. One thing that's kind of interesting to me about this picture is the bottom left, where you see some welded wire mesh, and obviously, in my mind, that was a shotcrete repair that's having issues. So it just reminds us that it's not necessarily the procedure or the process. You know, we need to really understand what the problem is as a starting point when we start to move forward with repairs. And so if you were in the earlier session, I showed the same flow chart, just something that we put together to show that it kind of starts with an understanding of the problem, you know, which leads into maybe some types of investigation, including concrete and corrosion testing, potentially non-destructive testing as well, understanding the cause of the problem, and then developing a repair solution that meets the needs of the structure, the needs of the owner within certain budget requirements, and that's all done by the engineers of record. That leads into repair strategies, and in this case we're talking about more specifically cathodic protection as one option that you may consider for longevity and durability of concrete repairs. If you're interested in this flow chart, it's available on wesavestructures.info is the website. So why do we use this repair? Each one of the repair application procedures follows a similar step-by-step categories. When do you use this repair? Use this repair to mitigate corrosion, and primarily we're seeing that due to chloride contamination when you have de-icing salts or atmospheric exposure to marine environments. Sometimes using contaminated aggregates is another issue. Sometimes you see carbonation as a source of the corrosion problem, which is more of a reduction in the pH around the reinforcing steel that occurs over time naturally. And sometimes you have a combination of chloride contamination and carbonation, which is particularly a bad situation. And we know that, through the years that when we repair structures that are particularly chloride contaminated, that are more aggressive, you are leaving chloride contaminated concrete in place. And you'll see periodic situations where you may see additional corrosion occur around repairs over time. And there's different terms that have been coined for that, ring anode corrosion, halo effect, patched accelerated corrosion, etc. There's just some pictures that we've taken through the years of the one up in the upper left is a bridge deck in Connecticut, where you see just a whole series of repairs over the years, and they have more areas that are marked off for additional repair. And just the process of doing the repair itself is necessary to provide protection to the steel in the area that you're repairing. Also provide surfaceability and safety for the structure, but it may not in and of itself be solving the problem. So one option, and there are other options as well that's used for providing longevity to the concrete repairs, is called using embedded galvanic anodes. And you see in this graphical illustration, you have a chloride-contaminated concrete. Those figures there are just general kind of indications of what the potential of the steel could be with regard to reference to a half cell. And the more negative the number, the more corrosive or the higher the corrosion potential. So you see that the chloride-free patch within the repair, it's electrically or ionically connected to the rest of the structure, which is still chloride containing. And in that situation, the areas around the patch will have a tendency to want to corrode. And by kind of artificially using an embedded galvanic anode in the repair, which has even a higher potential or more negative potential than the surrounding areas, that's going to want to be the first thing that corrodes relative to the rest of the structure. So it's basically trying to keep the anodic area, the area that corrodes, within the repair and not allow that to be transferred to other areas of the structure. So when do we use this repair method? Like I said, patch repair, primarily chloride contaminated or carbonated concrete. Also, in some cases, it's just not concrete repair. From a patching repair, you'll have lots of situations where you have joints that are established between new and old concrete. You think about expansion joint repairs. You have large slab replacements. Those slab replacements, for example, are connected into some exterior concrete or maybe into columns underneath. And the remaining concrete that's left in place has a potential for corrosion, then that may be a potential application. And you can also, on a different type of system, target corroding areas of existing structures, which we'll show that in a second here. So in the repair application procedure document, there's some nomenclature that you'll see that is used. And we're going to talk about two different types of anode systems. Type 1 is the anode systems that are used within the standard repair area. And the type 2 embedded galvanic anodes are designed to be installed into sound concrete as more of a proactive measure. So there's type 1 and type 2 embedded galvanic anodes, which are covered in the document. There's also some terminology with regard to the chemistry that's used for these anode systems. Type A, which are typically alkali activated systems, use a high pH environment around the zinc core. And then there's other systems which are more reliant on different types of salts to keep the anode active. So this is an example of a photograph of a project where you see a typical type of isolated concrete repair. One thing that's just really important to say is that embedded galvanic anodes are not solving an overall corrosion issue. If this whole structure is corroding, you may need to have a much more comprehensive approach. These galvanic anodes are really just designed to extend the life of the repair and provide localized protection around the repair area. So you see the steel's been cleaned, prepared. The galvanic anodes are attached to the reinforcing steel. And then in this case, you have the concrete repair in the bottom right that's been executed. Those situations, the zinc from the embedded galvanic anodes connected to the steel and the reinforcing steel. Zinc has a higher potential for corrosion. It starts to sacrifice itself, and the zinc becomes anodic, and the steel tends to become the cathodic area. Just more photographs of this type of application. This is a parking deck repair. You see anodes just placed around the perimeter. In these types of situations, you don't see them generally placed throughout the repair area in larger repairs because they're really just targeting to the hot spots. The hot spots is this interface between the new and old concrete. So you see them typically used around the perimeter. Balcony edge repairs, a lot of galvanic anodes used in the building repairs like this. These balconies that are along coastal areas. And then also precast targeted protection around weld plates where you have, joints in the precast structures, which tend to be a weak spot from a durability standpoint. If you need to do repair in localized areas, it's ideal application for these types of anodes. This is a slab replacement for a balcony. So instead of just doing a bunch of patching on the balcony, they decided just to do a removal of the balcony. So that's going to really solve the major issue of the corrosion because you're removing all the chloride contaminated concrete. However, where you have the bars that are penetrating back into the structure, just for added protection, you see a row of galvanic anodes that are placed along that interface between the new and the old concrete. And another example is adding on to a structure modifications. This is a bridge that is actually having an additional lane that's being added. And you see in the inset photo, you have existing bars which are coming out of the existing bridge deck. You have the couplers to the new bars, and you have this construction joint where you have a potential for penetration of de-icing chemicals or what have you into that area, and just a little bit of additional protection along that joint on a large project like this didn't really add much to the overall construction costs. We've had a lot of discussion in our committee about adding more videos, so and we're going to try to add more videos to our documents. So what I did is I added a video to our presentation here. Wow, it's loud. See if I can turn it down, but what you see here is two different types of attachment mechanisms. You have the anode on the left, which is using a single wire attachment. So we have one wire that comes off of each end of the anode. On the anode on the right, you have two wires off of each end of the anode. And that basically, each of the wires need to be wrapped around the reinforcing steel and then tied together tight. And so you see on the single wire anode, those wires are connected around and tied together and twisted tight. Thank you for helping me, whoever did that. So, these are basically a simple attachment mechanisms. The wires are embedded through the zinc anode within the system. So you get an attachment from the zinc anode to the reinforcing steel to make that electrical couple. I apologize for the video, it's a little jumpy. But once again, surface preparation is really important to get a clean bar. If you have a clean bar and you're attaching the anode directly to the bar, you have a steel-to-steel contact. It'll be a very good electrical connection. And you do want to verify that you have a good connection after the anodes are installed. So just move forward here. So that's give you an overview of the type 1 anodes. Type 2 anodes are used in a more proactive, targeted fashion. They're used and placed in sound concrete. So the picture you see here on this slide is from an application where the column was actually going to be strengthened with FRP, externally bonded FRP, and there was a corrosion investigation that occurred, and they discovered that the columns were actively corroding, chloride contamination. And so, in this case, the embedded galvanic anodes, the type 2 anodes, were proactively installed into the column to provide protection that would last for underneath of the FRP system. So this is one application of a type 2 system. Once again, another application would be for using type 2 anodes to target into hot spots as determined by a corrosion potential test. So this is a parking structure. If you do an investigation, generally not the entire structure is going to be corroding at the same rate. You're going to have areas that are corroding faster than others. If you can identify those by corrosion testing, in this case it was through corrosion potential testing, then you can proactively install type 2 galvanic anodes into the hot spots from a targeted fashion. If the entire structure needs to be protected, you may use other types of cathodic protection systems would be possibly considered. This is a type 2 anode that's used to protect a column in an industrial plant. And you see this, the column thickness is such that the anodes are basically being installed in from one face of the column and placed in the center of the column, and you see a grid pattern of anodes protect the entire column. So this is another video that gives you an idea for installation of a type 2 anode.
This video demonstrates the installation of a GalvaShield CC anode. Rebar should be located and marked on the concrete surface. The rebar connection hole is drilled directly to the reinforcing steel adjacent to the anode location. Clean out the connection hole. Drill the anode hole in close proximity to the reinforcing steel connection. Check to ensure proper fit. Make a saw cut groove between the anode hole and the reinforcing steel connection hole. Clean holes of debris and dust. The anode lead wire shall be electrically connected to the rebar connection hole. Confirm electrical continuity between the anode lead wire and the reinforcing steel. Fill the bottom 2/3 of the hole with mortar. Insert anode into the hole and apply pressure, forcing the mortar to fill the annular space around the anode. Make the connection between the anode and the anode lead wire with the chosen connector. Cover the anode and lead wire with embedding mortar. Finish flush, ensuring a minimum of 1 inch cover over the anode.
Okay, the key point here is that even though these anodes are installed proactively into sound concrete, they still need to be connected to the reinforcing steel. And that's one way that you can make those connections, one method. One thing we talk about with using anodes with regard to the type 1 anodes is materials and equipment. One thing, if the anode is going to go inside the repair material, we want to make sure that the repair material or the anode spacing is such that it is conductive within the material, because you want to protect the areas outside of the patch. And it's not a complicated process with regard to materials. Safety considerations. Anodes, can be alkaline in nature, just similar to concrete. So we just be careful. Read the SDSs for the products that you use. Make sure you use protective clothing. Checking the repair. Most of the projects will have some type of quality control procedure, and the primary quality control procedure is to check the continuity of the steel within the patch, and also check the continuity of the anode to the reinforcing steel. And I have a slide to kind of show this. So this is an anode that's connected to the reinforcing steel. You're taking a simple voltmeter, attaching it to the lead wire that's coming off the anode, and you're attaching it to the reinforcing steel. You're checking for the voltage or the resistance between those two leads, and if it's good contact, there'll be no resistance to speak of between those two materials. If you have a higher resistance, you may still have some oxides on the steel that need to be cleaned, and then the anode reattached. So anyway, that's a quick overview of repair application procedure number 8 for embedded galvanic anodes. Thank you.
What does the anode consist of? Is it zinc? And how long does it last? And then what happens when it's used up? Is there a void in the concrete?
Okay, that's a really good question. So the embedded galvanic anodes are zinc. If you just take the zinc by itself and you put it into concrete, even though concrete's alkaline, it's going to be relatively passive in the concrete. So all of the embedded galvanic anodes have some type of covering material on the anode to create an environment that keeps the anode active. Those covering materials or mortars are they contain the chemistry that keeps the anode active, but they're also relatively porous. So when you connect the zinc to the steel, the zinc starts to corrode. The corrosion byproduct of the zinc starts to move into the porous mortar that surrounds the anode. So, you know, how long the anodes last is basically based on how many that you use for the amount of steel you're trying to protect. If you use larger, there's different sizes and shapes, but for most situations, you're probably looking at something that's going to last between 15 and 30 years in place. I think more commonly you see 10 to 20 years as kind of a number, and that all depends upon if it's an aggressive marine environment or if it's a drier bridge environment or what have you. At the end of it, you don't really end up with a hollow where the zinc is consumed. It's basically filled with the corrosion byproducts of the zinc. So it's not like the zinc disappears. It's basically being converted into the corrosion products of the zinc inside the anode body. So,
All right, thank you.
Yep.
On some of the examples there where you're showing the bridge deck extension, et cetera, they're just, your anodes are just kind of just floating in space and it's going to get cast into new concrete. We've been finding when we're doing, especially with the SECs, that kind of stuff, concern about the resistivity of the concrete. Are you finding that most, like, I'm assuming for that type of concrete, using a fairly high quality 35, 40 MPa with low chloride, low chloride resistivity, permeability, et cetera. Are you finding that most concretes are still okay with these anodes, or do you have to somehow specify a low resistivity for those bridge deck type applications?
Okay, that's a good question. You know, if there's no exact pass-fail. It's all a matter of degree. The higher resistance the materials are, the more, you know, restricts the current that's being developed. If you have a situation where the resistivity of the material starts to become too high, then there are some alternate application methods, and many times what they'll do is just put a little mortar bridge of normal resistance mortar between the anode and the substrate to create a little conductive bridge in that situation if the material resistivity would be too high. The other option would be to take a type 2 anode and install them into the sound concrete along the bridge deck, but in the original section would be another option to consider.
All right. Thank you, Chris.